Okay, yes, we'll do some new stuff now, and this is going to be introduction to rings and fields. Oh, sorry. Introduction to rings and fields. And now, so far, with groups, we had one binary operation. And now we're going to look at structures that have two binary operations. And usually we call these, just for simplicity, we call them addition and multiplication. Even though depending on what you're dealing with, it may not, they may be something else, but just when we do like the general proofs and stuff, we call them addition, and sometimes there will be addition multiplication, but sometimes it could be other operations, but multiplication. So now we're going to start dealing with things that have two binary operations. And then, so the first thing we're going to look at is a ring. So definition of a ring. And so a ring, and usually maybe represented maybe like this with a plus and maybe a dot to kind of be indicate multiplication, and operations could be something else, is a set are together with two binary operations plus and that. Again, I'm repeating this up, but I just want to put it down to have it coherent, which we call addition and multiplication. Defined on R such that the following axioms are satisfied. And so one, now this set under this first operation, so this R under that, like say under the addition, is an abelian group. So in other words, if you just took that first operation with this set, that would form a group, and in fact, it would be an abelian group. And so number two, a multiplication is associative. So once again, you would have, just like we had before, again, whatever your binary operation is, since we're calling this multiplication now, is going to be equal to A dot B dot C. And then the one kind of different thing is the left and right distributive laws hold. So that would mean that so where you have both operations, just like distributive laws that you had like way back when, you can distribute with your second binary operation. That. So for something, so again, a ring has two binary operations, call them addition and multiplication. And under addition, this set isn't formed an abelian group under addition. Multiplication's associative, and the left and right distributive laws hold. And just to give some examples, the integers under addition and multiplication, the rationals, the reals, again, remember this means rationals. These are all rings. And again, remember, under the second operation, it doesn't have many requirements, just for it to be associative, and that the distributive laws hold. For example, it doesn't have to have an inverse under multiplication or anything like that. So these are all rings. And then we have another definition for homomorphisms of rings. For rings. And once again, when we say like R and R prime, these just mean two different rings. a map say from the one ring to the second ring is a homomorphism if the following are satisfied. For all A and B in the ring. And in some ways, this is even clearer than the homomorphisms that we had for groups, because this really makes it clear. Is it's really saying that under the one operation, this is true, and under the other operation, it's also true. So if you have, say, A, B, like this. So if you have a ring, it just has to, mainly what it has to be is a homomorphism under both operations. And then we have some other definitions here. Against some of these get very similar. We had a before with groups. Again, this is this would be like, say, a ring isomorphism. And isomorphism from a ring to R to a ring R R prime, I should say, is a homomorphism.
Should that be the other way around?
I'm sorry.
Should it be a homomorphism from a ring to another ring is an isomorphism if something is true?
Oh, yeah, let's see. How did I state this? And it's from a ring. Yeah, I think I sort of stated it's kind of odd. I sort of stated this an isomorphism. Uh, okay, yeah, I kind of I'll show you what I did. It sort of make a little bit of sense, but yeah,
Oh, never mind.
yeah, you said yeah. Though it is kind of odd, I kind of reversed it. So isomorphism from a ring to a ring is a homomorphism that is one-to-one and onto R prime. But yeah, would though I see what you're saying, it would have been like a little sort of make a little bit more sense if I said, oh, a homomorphism that is one-to-one onto is an isomorphism. I sort of say that sort of a little bit in reverse. So yeah, an isomorphism from ring is a homomorphism one-to-one onto. Similar to what we had with a group, if a homomorphism one-to-one onto, it'll be an isomorphism. And then in this case, we say the rings are R and R prime are isomorphic if we have such a if such an isomorphism exists. And again, fairly similar we had before. So again, so we have a ring. And then now, another thing that we have is let me leave that here. And another thing that we have is a commutative ring. and this is basically a ring for which the multiplication is commutative. So as we said, automatically the ring is commutative under addition. Remember, we said that's one of the definitions of a ring is that under the first operation, which you call addition, it's abelian, so it's commutative under addition, but doesn't necessarily have to be commutative under multiplication. But if it's a commutative ring, it is commutative under multiplication. And then now this is another definition, the multiplicative identity and again, let's say we call it 1, which we normally have for multiplication, is called unity. So again, under the group operation, like say the first operation, we call the identity, but usually under the multiplicative identity is called unity. So that leads to another definition. Remember, though, the ring does not have itself, if it's just a ring, it doesn't have any identity. Remember, like the way we defined it, the ring does not have identity under the second operation. Of course, it will under the first operation because it's a group. But then there is if it does have an identity, what's called a ring with unity. So a ring with multiplicative identity, which we call unity, of course, is a ring with unity. And that's what's, again, that's the definition. If it happens to have a multiplicative identity, it's called a ring with unity. And so then more definitions, some of these may seem kind of odd. Definition of what's called a unit. And so if you have an identity ring, so let R be a ring with unity, And again, sometimes we symbolize the unity as one. And again, we're going to say the specific case where it's not going to be equal to 0. There's going to be some odd cases where that's going to be true. An element U is a unit of R, of the ring R, if it has a multiplicative inverse. Now we're looking at a specific element. So here we're kind of assuming that, again, we have a ring with unity, so it has a identity. And then if an element in that ring has an inverse, then we call that a unit. Again, if it has a multiplicative inverse. Then we have what's called a division ring. And again, if every non-zero element of the ring is a unit, again, remember that just says has a multiplicative inverse. If every element has a multiplicative inverse, then R is a division ring. So it's another another one. So so again, if every non-zero element of a ring is a unit, in other words, if every element has a multiplicative inverse except 0, we're kind of eliminating 0, then this is called a division ring. Then finally, the highest, sort of like the highest structure we have is a field. And this pretty much has everything in it. A field is a commutative division ring. So again, it's a lot of definitions, a lot of sort of odd definitions in some cases. But so there's things that there are certain structures that have some of these things and not others, and so they have all these different classifications. Again, like real numbers under addition multiplication, they're a field, and also complex numbers is also a field. And let me see. Yeah, I was thinking, yeah. So any questions on any of that? All the sort of strange definitions. So now, if you do have a lot of times, again, you don't always have to do all these tests, to see if you have like a ring and stuff like that. You can do like just like we had for groups. We have like subring tests. So, and just like before, we'll have like a definition of a subring. And again, remember this is a ring. So a subring of a ring is a subset of the ring that is a ring under. Now, this is a lot of times what they use. They'll say under the induced operations from the whole ring. It just means the same operation. I'll put it this way because a lot of times when you see in books, it'll write that way, under the induced operations. Again, the same operation. I put in parentheses, same operations. From the whole ring. And again, just saying that if a subring is a ring, again, a subring of a ring is a subset of a ring that is a ring under the same operation base, just like we had for groups. Again, like I said, sometimes you can identify something to be a ring, and it may be a subring of something else, and you don't necessarily have to say it. But again, if you know that it's a subring, it's just sometimes helpful. And then, of course, just like before, we have like a subring test. And so this is a theorem. So again, rather than go through all the steps that you have to go through, because again, to prove something is a ring, you have to prove it's a group, it's a abelian group. We have to prove that it's the distributive laws hold, multiplication is associative, all those things I listed there. And but if you know that it's a subset of a ring, then you can just do this test. A non-empty subset S of a ring R is a subring of R if and only if for all A, B, in S. So again, we have a non-empty subset of a ring. Again, we don't yet know that it's a ring itself. That it is, but it is a subring. It is a ring. If and only if for all A and B and S we have that number one, A minus B is in S, which I guess would be that if you take, so you could sort of say it this way. So like A minus, but it's almost like saying A, B inverse, just like we had before. Again, it just depends upon which operation. A lot of times they write it this way because they kind of call the first operation multiplication. So they're saying like A plus the inverse of B is this, they'll say it maybe this way, or you can say it this way, is in S. And then under the second operation, AB is in S. Amazingly, again, it'll be a subring if these things are true. Now, of course, a lot of it makes sense because if you have a subset, and the original set was a ring, it was a commutative group. It was an abelian group. So you don't have to check to see if things are going to commute, because if the members commuted when they were in the original ring, they're going to commute when they're in the subgroup or in the subring. So you only have to check. So again, what is nice with these kind of tests is you don't have to test a whole bunch of things. If you know your set came from a bigger ring, then all you have to do is test those two things to prove it's a subring. And then same thing with a field. Again, the field is kind of the most advanced structure that we have. And then a subfield. Oh, let me put that back up. Sorry about that. And while you're copying that, next thing we have is a subfield. So a subfield of a field F is a subset of F that is a field under the induced, again, I'll use that word again, induced operate, again, the same operation. So just like with the subgroup or a subring, a subfield is simply a subset of the field that is a field on its own as well. And again, we have these tests. We have a subfield test, a non-empty subset S of a field F is a field and do the same two operations of F, sorry, of F, if and only if for all A and B in the subset, we have again A minus B in S, and then 2 for B not equal to 0, AB inverse is in S. Yeah, I guess probably on the last one, when I had for the uh yeah, probably in this last one, it might be a little bit misleading. Uh, yeah, maybe if you look back at the subring test, I probably shouldn't have put this in parentheses because we are assuming the first operation is going to be addition. So maybe I put in parentheses this, but I probably shouldn't do that because we're assuming that's going to be. So let me just cross. So if you go back to that subring test, cross out what I put in parentheses there. Probably should just leave it here because that's right. We are distinguishing specifically that the first operation is kind of multiplication, or at least we're, excuse me, first operation addition, and second operation we'll call multiplication. So yeah. So yeah, if you go back that subring test, let me just leave it there without having this in parentheses here. I was that's probably not, it's I guess technically okay, but that can be a little bit misleading. Because then when we get to the subfield test, then we really do need that other operation. So, and really this is going to be, you could even, if you want to make it real clear, for this one, you can also put the dot here. This is going to be under multiplication. So really, again, what's really nice about these tests, we had all those things that led it up to what a field had to be. So you could test all those different things, which would take you quite a while. But if you know something's a subset of a field, all you have to do is verify these two things. That if you take for all the elements A and B, if you take A plus basically B inverse under addition, which is going to be negative B, that's going to be in the set. And if you take A times B inverse, which would be in this case the multiplicative inverse, that's in S. That's all you have to do to test that you have a subfield. Any questions on any of that? Any questions at all? And there's some calculations things that examples we can do. We'll probably do this next time. Maybe do some more definitions right now. Yeah, we do some more definitions here. Or and maybe call this characteristics of a ring. And get a definition. If for a ring R, positive integer n exists such that n dot a is 0 for all a in the ring, then the least, and you can maybe say the smallest such positive integer is the characteristic of the ring R. So if there's a number, again, a positive integer such that if you take that positive integer times every element in R and you get 0, then the smallest of those is going to be called the characteristic. And again, if no such integer exists, then R has what they say has characteristic 0. That's usually the way they say it. Or sometimes they'll say the characteristic of R is 0, or just say R has characteristic 0. So if there's nothing that's going to be true. And so that's another definition. So actually, let me then, so again, we'll do some number stuff next time, but let me apply some of these tests. So let's take a look at, say, one like this. Consider the set 2Z. Of course, that's going to be the set. We have -6, -4, -2, 2, 4, 6. Like this. Show that this is a ring. Now we didn't actually prove it, so we probably should have, but we did state before that recall that the under addition and multiplication is a ring. And 2Z is a subset of Z. So we can use the sub ring test. So again, and let me just put in parentheses here. So we just use sub ring test, like, so that just to keep it in front of us, AB for all A, B, and 2Z. In our case, let's say we have A minus B is going to be in 2Z, and then A times B is going to be in our 2Z. So that's what we're going to have to, we'll use that. Remember, that's our subring test, whatever this for all A and B in the subset. If we show A minus B is in the subset, A times B is in the subset. Now in our case, so let's sort of do that formally. So again, what I'm going to do, now usually you can use A and B if you want here. I'll use, since we know these are going to be integers, a lot of times we use M and N for integers. So, but you could use A and B if you like, whatever you're most comfortable with. But so let M and N be in 2Z. So in other words, so to do this first test, we have to try two typical. Remember, if we have to show that something is true for all A and B, we just have to take two typical elements. So it's an A and B. And then let's check this first thing. If we take M minus N, and now the question is, if you take two typical elements and you subtract them, will they still be in 2Z? And of course, the question is, it's good. The difference of two even numbers is going to be even, right? So this is going to end up being even. So therefore, if it's an even, if the difference is going to be even, then that's going to be in 2Z, right? So that looks like it passes that test, if that makes sense. And the other thing we have to check is this over here. Then check N times M. And again, if you multiply two even numbers, you get an even as well. And again, if it's an even number, it's going to be in this set. So yeah, so this is, so this is a ring, or a sub, you can call it a subring. Any question on that? You can see, so in this case, it's really pretty simple. Is the fact that just take two typical elements and say, okay, is that typical element going to be in the subset? When we take the M, the difference of the two, and we multiply them, is that going to be in this subset? Any questions on that? And let me do another one here. And let's do another example. So let's say S is in MN. So it's going to be this set such that N is odd. And so under addition and multiplication, is this a ring? Or subring. So once again, we said before, notice that these are all elements from the rationals. So this is a ring. So we can use a subring test. Because S is a subset of Q. And so let's just go with this. So let X and Y be an S. Then that's going to mean that X is going to be equal to M1 over N1, and Y is going to be equal to M2 over N2. Again, so we're picking for M1, M2 are going to be in the integers. Now, we have to specifically say the denominator is going to be odd. And for 1, 2, and let me say this, let me say odd integers like that. So if we pick two typical elements, we're going to have N1, N2, it's going to be the denominators. Those are going to be odd according to our group here. And so let's do our test. If we take X minus Y, that's going to be M1, N1 minus M2, N2. Now, if we add these together, we'll make a common denominator, N2, M1 minus N1, M2, and N2. And let's see, if we multiply two odd numbers, we're going to get an odd number. Is that right? So two odd numbers are going to be odd. So this is going to be odd. So that's going to be in S, huh? Because, see, the numerator is still going to be an integer, like we had up here. And the denominator is going to be an integer as well, but it's going to be odd because we took two odd numbers, multiplied them together. So therefore, this typical element is going to be in the set S. So it passes the first test. Then if we do the next test, and once again, this is going to be odd, and the numerator is going to be an integer. So therefore, that's got to be an S. Because according to our what's in the group here, we have an integer divided by an odd integer. So we put these together. So this is a subring. And we're over time.